Welcome to this lecture series in group theory. Last time we looked at the notion of a subgroup. So suppose we have a group G and we are given a subset of it. Then we call it a subgroup of G if first of all it is closed under multiplication, which is a short form of, or rather a colloquial way of saying this. And further, the restriction of this binary operation 2H cross H is a group, and this restriction is legitimate because of 1. Alright, so that's the definition of a subgroup, and we saw that if H is a subgroup of G, and this is the notation for subgroup, this less than equal to, then EH equals EG, meaning the identities coincide. And further, if you have any element in H, then its inverse is unambiguous, meaning you can take the inverse in H, or you can take the inverse in G, but those two are the same things. So we do not need to qualify this with a subscript or anything. This is just an unambiguous thing. Lastly, we saw a criterion to check whether or not to check if a given subset is a subgroup. So you take a subset of a group, and then it is a subgroup if and only if it is closed under multiplication and it's closed under inverses. So that's the gist of the previous lecture. And now let us, so these are the problems, and these are actually quite interesting. So we will probably cover these later in lectures, but right now I've given them as exercises. The third exercise says that if G is a finite group, then to check for to check if a given subset is a subgroup, one does not need to check for inverses. You just need to check that it is closed under multiplication. So for finite groups, the situation is even simpler. All right. So this lecture is all about examples, and let's start with some very simple examples. So we have R, which is a group under addition, and Q is also a group under addition, so is Z, and these are subgroups, and you can check that. Since closure under addition is clear, you add two integers, you can again get an integer. Inverse is also clear. If you take an integer and take the inverse, then it's minus n, which is again an integer. So it's just a very simple check. So this is there. Trivial subgroups, well, if G is any group, then this is a subgroup, and the whole of the group is also a subgroup. So this is the trivial group. I don't know what's the name of it. I think people just generally refer to it as the trivial group. And well, this is also in some sense a trivial group, a trivial subgroup, because it's just not giving us anything new. So one can easily check that these are actually subgroups of the original group G. All right, another somewhat silly example is this. So what is 2Z? 2Z is, let me use a different color. 2Z is all the even integers. So it's 2n in Z. And if you add two even integers, you get an even integer. So you invert an even integer, you get an even integer. So therefore, these are also subgroup. This is also a subgroup of Z. Yeah, so we were talking about Z under addition. Okay. Similarly, DZ is a subgroup of Z, where D is just any integer. All right. It could also be 0. In case D is 0, then this is the trivial subgroup. All right. Fine. So these are some very simple examples. Now for a little bit more interesting examples. We have R star, which is a group under multiplication. And this is a subgroup of it, because you multiply 1 with 1, you get 1. You multiply minus 1 with minus 1, you get 1. You minus 1 multiplied by 1 is minus 1. So it is closed under multiplication. And inverse is also it is closed, because if you invert minus 1, you get minus 1. If you invert 1, you get 1. We are talking under multiplication. So that's a subgroup. This is also a subgroup of R star under, well, R star is a group under multiplication. So this is also a subgroup, because if you multiply two positive integers, you get a positive integer. You invert a positive integer, you get, so what did I say? You multiply two positive reals, you get a positive real. And you invert a positive real, you again get a positive real. So it checks out. This is a subgroup. And this one I find the most interesting amongst all these three is we have this complex plane. So what did I do? we have this unit circle in the complex plane. S1, yeah, so what is S1? S1 is all complex numbers. I've said this before, but no harm in repeating. So this is all complex numbers with magnitude 1. And the complex plane we imagine like this whole expanse. And if you take away the origin from C, then what you get is C star. So what is C star? C star is all complex numbers which are non-zero. And this is a group under multiplication, usual multiplication of complex numbers. And S1 is a subgroup. Because if you multiply two unit magnitude things, you get another unit magnitude thing. And you invert a unit magnitude thing, you again get a unit magnitude thing. So that's very nice. Okay. And this is one of the best examples. Is the orthogonal group is a subgroup of GL2R. Again, there's not much to do here. Basically, if you compose two orthogonal transformations, let me write H for O2R and G for GL2R. The only thing is that, well, O2R is already a group. Group under what? Under the same binary operation as that of GL2R, the binary operation being composition. So that's it. I mean, we do not need to go by the criterion to check whether or not it is a subgroup. It is a subgroup because if you restrict the binary operation of GL2R to O2R, you get a group that we already know because O2R is a group. So that's a very nice example, and this was the motivating example that we gave when we introduced the notion of a subgroup, is that O2R is preserving a little bit more than just linearity, and hence it is supposed to be a subgroup. Here we can see geometrically that it is a subgroup. All right. Matrix groups, well, you take a field F and fix a positive integer, then all the n cross n unitriangular matrices is a subgroup of the n cross n upper triangular matrices is subgroup of n cross n invertible matrices. Why? Because, well, the binary operation is same, the multiplication, and we already checked that these are groups. Each of these are groups. So the subgroup thingies hold because this is contained in that, this is contained in that. So that's very nice. Now let us look at some abstract examples. So suppose we have two subgroups of a group G and assume G is abelian. So let me remind you what that means. That means that that means that xy equals yx for all xy in G. That's what abelian means. So if you have an abelian group and two different or two possibly same subgroups, then you define this set, this is the definition, as sum of two elements, one from the first one from the second one. So this is a subset of the group G. Then the fact is that this is actually a subgroup of G. So here I think it helps to use the criterion. Proof is very simple. If you have, let's say, x and y in this, then x is x1 plus x2 with x1 in h1 and x2 in h2. And similarly, y equals y1 plus y2, y1 in h1, y2 in h2. And I'm not saying that these x1, x2 are unique. There could be multiple things, but we have just chosen one such x1 and x2 such that x is equal to x1 plus x2 and so on. Okay, so what is x plus y? X plus y is x1 plus y1 plus x2 plus y2. But now since h1 is a subgroup, x1 plus y1 is an h1 and x2 plus y2 is an h2, and hence this is an h1 plus h2. So what we have shown is that this is closed under the binary operation. h1 plus h2 is closed under binary operation. So yeah, I should have mentioned that when we are talking about abelian groups, we generally use this plus symbol to denote the binary operation of the abelian group. We do not use the multiplicative notation generally. There's nothing wrong with it, and you can use the multiplicative notation. but generally we use the additive notation whenever we're talking about an abstract abelian group. I should have mentioned that earlier, but anyway. So we have shown that this thing is closed under the binary operation. And what about inverses? Let's take x inverse. So just note that x1 inverse, where this inverse has been taken in h1. Well, sorry, I should not say that. So wait. So we have x is something in h1 plus h2. We want to show that its inverse is also in h1 plus h2, and it's just simple to check that its inverse is nothing but the inverse of x2 plus the inverse of x1. So there is no ambiguity about the inverse of x2 or anything, because x2 is an element of G, its inverse is well defined. Even if you think of it as an element of h2, doesn't matter. We have already shown that inverse taken in a subgroup is same as the inverse taken in the bigger group. So just check that this thing is a let me not write it that way because the group is abelian. Let me write it x1 inverse plus x2 inverse. So this thing is actually an element of h1 plus h2, because this is an h1 and this is an h2, and one can check that this is inverse of x inverse, and that's it. So this guy is closed under inverses also, and therefore is a subgroup of G. And let me just remark that this can be generalized to non-abelian groups, this kind of thing, but we need an extra hypothesis on that, and I'm sure we'll cover that in due time. But right now, this abelian example is good enough. Okay. This is another very interesting example. You take any two subgroups of a group, their intersection is again a subgroup. So why? So let x and y be in x intersection h intersection k. Then we want to show that xy is also in h intersection k. But in particular, since x and y in h, we have xy in h. X and y are in h intersection k, and hence in particular they are in h. H is a subgroup, hence the product x and y is also in h. Similarly, the product is also in k, and hence the product is actually in the intersection. So h intersection k is closed under taking products, or more properly, it's closed under the binary operation of G. All right, what about inverses? Well, let x in h intersection k be arbitrary. Then x inverse, well again, so since x is in h intersection k, it is in h, and hence its inverse is also in h because h is a subgroup. And similarly, its inverse is also in in k, because k is a subgroup, which implies x inverse is in h intersection k. So that's it. Therefore, this is closed under the binary operation as well as taking inverses, and hence this is a subgroup. Great. Another very interesting example is subgroup generated by a subset. So before I get there, let me generalize the previous one to prime. Is let h alpha in J be a family of subgroups of a group G. So what do I mean family of subgroups? Basically, I'm not saying that we have only finitely many subgroups. It could be just some arbitrary collection of subgroups of a group G. So then the intersection is also a subgroup. And it's the same proof as the previous one. I will leave this as an exercise. So here is the thing. Subgroup generated by a subset. So what is the definition? So let S be a subset of a group G. G is a group. And let, what should I say? Let script H be all those subgroups of G. So all those, let me write it. Yeah, fine. So all those subgroups of G such that S is contained in H. So collect all those subgroups which contain the given subset S. So first note that H is non-empty because the whole of the G is in script H. And now we define this angular bracket S as the intersection of all the things in script H. All right. So this is the notation right now, and that is defined as this particular subset of G. But this is a subgroup of G because each element of script H is a subgroup of G, and as we just saw, their intersection will also be a subgroup. So this is what we call the subgroup generated by S. And if this looks super complicated, basically what we are trying to capture is, this is philosophically supposed to just mean the smallest subgroup of G that contains S. So now if you look at it in this light, I am sure this will make much more sense. Why are we doing what we are doing? Okay. A special case of it, an important special case, is the subgroup generated by an element. So let G be a group and X be an element in G. Then this is the, I mean, there's nothing to say. This is just the subgroup generated by the singleton X. So this is a another notation. Rather than writing this, we just write that. So this is an interesting, or at the very least quite important way of getting subgroups, as we'll see. Okay, and I think that's it. We will see more examples as we go along, but for now I think this serves as a good set of examples. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.